So we're going to get started. It's a great pleasure to have Amit Singer this afternoon. Amit is associate professor in the mathematics department at Princeton University. He received his PhD from the University of Tel Aviv in 2005. His work was awarded a very prestigious prize in Israel for the best mathematical dissertation from a country that generates some of the best mathematicians in the world. This is a great honor. He moved to the US and was a Gibbs assistant professor at Yale for 3 years, and then joined Princeton. He's a Sloan Research Fellow and a recipient of the Presidential Early Career Award for Science and Engineering. Please welcome Amit.
Okay, thank you, Francois, and thank you for inviting me to be here. I'm honored to be here. The title of the talk today is Vector Diffusion Maps and the Connection Laplacian. It sounds a bit mathematical, so I would like to start actually from a motivating problem in structural biology. So the goal in structural biology is to find three-dimensional structures of molecules. And classically, the way people have found structures is using X-ray crystallography. But in order to be able to do X-ray crystallography, you need to find physical conditions in which the molecules would like to arrange themselves on a regular grid, lattice, all of them pointing in the same direction. And often this is a very daunting task that people do not know how to do. So there are many molecules of biological interest that people do not know how to crystallize. So instead, biologists came up with an alternative technique, which is called cryo-electron microscopy. And the idea in cryo-EM is instead of crystallizing the molecules, you just freeze them in a very thin layer of ice. So the ice layer is very thin, like of the order of 100 nanometers in width. And you bombard electrons vertically to the ice layer. Beneath to the ice layer, you have a film or a camera. And every pixel, its intensity is proportional to the line integral of the electric potential created by the molecule, if there is a molecule there, in this vertical direction. Now, at the moment of freezing, all molecules just pick some random and unknown orientation. So think of it as if you have like a planar soup of molecules that are embedded in this ice layer, each of which have exactly the same 3D structure. They look the same, but all of them just have, each of which has different orientation that we don't know. And the ice layer is so thin that actually in the vertical direction you would see at most one molecule. So no two molecules can fit in that direction. So mathematically we have a collection of images, say n images, that we denote by pi. I is just the index of the ice image. And the xy pixel, so we have x direction and y direction. And the xy pixel, it is proportional to the line integral of the electric potential of the molecule that is unknown to us, phi. That's something that we want to reconstruct. And we integrate in the direction of the third column of the rotation matrix. So what is this rotation matrix? This is an element of SO3, the special orthogonal group, rotations in 3 dimensions. So we have 3 columns, so you can think of it as a 3 by 3 orthogonal matrix with determinant +1. And the first and second columns just form a basis to the plane of the image. And the third column is just the imaging direction. And so we integrate in that imaging direction. But it's not just a pure integration. We also have noise that I'll explain later where it's coming from. And so the goal in cryo-EM, you can think of it as an inverse problem in which you want to find the structure of the molecule. You want to find phi, a function of 3 variables, x, y, and z, from the projection images, P1 to Pn. Now, in classical computerized tomography, that is very much related to this problem, for example, in medical imaging, when you want to find the 3D, say, density map of the brain of a patient. So the patient goes into the CT machine, and he or she are being told not to move for the duration of the imaging process, and the machine scans the brain from different directions. The reason why the patient is not moving is that so that the imaging directions are completely registered and known to the machine. But here, with the molecules, we cannot give the molecules instructions when they're being frozen. And so we get a collection of images in completely unknown viewing directions. So if you can somehow reduce the problem and find from the projection images themselves the underlying rotations and also positions, then we have reduced the problem to a classical computerized tomography problem. Then we are in a very comfortable and familiar situation. But in the cryo-EM problem, the rotations are unknown to us. And so one can consider this as a more difficult inverse problem to be solved. So to give you an idea what cryo-EM is all about, so in the very clean and say, toy example, suppose that you have 12 projection images, like the images that I'm showing you here, and the goal is actually to find a structure. So the 3D structure is unknown, and you want to uncover it just to reveal it from projection images at unknown directions. So here, if you look at the images, you can almost guess what is the volume. So like from this image, we can guess that there is a cartoon image that we are all familiar with. But in reality, things are much more difficult. And the reason why they are much more difficult is because of noise. So what I'm showing you here are 4 sample images out of a collection of much larger collection that consists of 27,000 particle images, each of which is of size roughly 100 by 100 pixels. And I hope that you can appreciate the very high level of noise in these images. So if you just look at pixel-wise, the signal-to-noise ratio, the SNR, is much below 1. And so you can ask, actually, how they pick particles. So the first thing that one has to do is some kind of image segmentation. You look at a very large micrograph, say 4,000 by 4,000 pixels, and the first thing that you have to do is to come with electronic scissors and to cut little boxes of, let's say, size 100 by 100 pixels, where you believe particles are located. I will not discuss this image segmentation problem, which is the first task in cryo-EM, but I hope that you can see that near center, the image is slightly brighter than near the corners or the boundary of the images. And that's actually what guides them in choosing the particles. But our task for today is to understand how can we take a data set of 27,000 particles that look like this and get a 3D structure. I'm not sure that I'll be able to tell you all my tricks in my bag, but I'll try to be as thorough as possible. And just to show that this is indeed possible, I'm going to show you now a movie that 2 of my students, Lanhui and Jane, did. And what you see in this movie is 2 structures, one in yellow, one in white. The yellow one is the ground truth. So luckily for the subunit, the 50S subunit of the ribosome, we know the structure, the 2009 Nobel Prize in chemistry. But it is shown here at the resolution of what we can actually reconstruct. And in white is actually our reconstruction from the same noisy images that I showed you at the beginning. So I hope that you can actually see, I can show this movie again, that the 2 structures are very, very similar. So to the naked eye, except for some noisy features, they look very similar. The resolution that I'm showing you here is about 20 angstrom. So, and now I have to tell you how we get to this structure. So the main focus of the talk today will be on a procedure called the class averaging. And that's a procedure that is intended to reduce the level of noise in the images. That is to do denoising through averaging. And the reason why I chose to focus for this talk on this procedure is because it is actually relevant to many other data analysis problems or even imaging problems. Whereas the other part of actually how to find the 3D structure is perhaps more particular to the cryo-EM problem itself. So I chose to focus on the class averaging problem. So what is the class averaging problem in cryo-EM? The idea is how to get rid of noise, averaging. So what we would like to do is to find images somehow that were taken from roughly the same viewing direction. And we know that if 2 images are taken from almost the same viewing direction, then the images should look almost the same, but maybe up to some in-plane rotation. And so if I'll take 2 pictures of, say, of Ariel now, and 1 picture like that and 1 picture like that, the 2 images will look exactly the same up to in-plane rotation. And so what I'm showing you here is an illustration with simulative data. So I just took a clean projection of my volume, and I show it to you here after I added Gaussian white noise at a signal-to-noise ratio that is not too bad, so you can actually see the resemblance between that image and the original one. And then there is another image where I just rotated this picture by 90 degrees and added a different realization of noise. So now suppose that these 2 images appear in my large data set of 30,000 images. can I find these two images, identify that they were taken from actually the same viewing direction, and then solve the in-plane alignment, rotate them accordingly, so after averaging, I get a much nicer image where the features are more pronounced and closer to the clean image rather than each one of the noisy images to begin with. The difficulty in solving the cluster averaging problem, there are two obvious difficulties. One is the very bad SNR that we have in our images, and the other one is computation. We have a huge data set. We have like 30,000 images. Some data sets have like 100,000 images. So how are we going to compare such all pairs of images in such a huge data set in a reasonable time? So what people do now is some kind of a clustering method where first they define what is known as the rotation invariant distance. So what is the rotation invariant distance? You pick two images like Pi and Pj, and you just try to solve the registration problem between them. That is, you brute force, exhaustively try all possible in-plane rotations, and if you also care about small translations, you also include that into the minimization process. And the distance itself can be Euclidean distance, but it can be other distances, other metrics that you believe are good for the data set. I will not talk too much about it. And once they are aligned, in the sense that they minimize this distance, you declare this to be the rotation invariant distance between image I and image J. So in that way, if you can actually do it for a large data set for all pairs of images, you get a matrix of dissimilarities between all pairs of images. And so then you can say, OK, if the signal to noise ratio is not too bad, what I would actually like to do is average. If I'm image I would like to average myself with my neighbors. Because small rotation invariant distances are an indication for similar viewing directions. But since we know that noise is our enemy in this problem, and probably will have many outliers, what they suggest is instead to use this matrix of dissimilarities and try to cluster it. And this will give us a better notion of clusters and neighbors. And so when you try it you can try it at home, simulate images, add noise. You see that it works very well at some high level of SNR, but at some point it breaks down. And the question is, can we do better than this clustering method that involved the rotation invariant distances? And first I would like to give you an idea how to think about this problem in terms of a graph. So one can associate a graph with the data set of images where the vertices, the nodes of the graph, correspond to the images themselves. That is, every vertex corresponds to an image. So if we have n images, we have n vertices. And we're going to put edges between any two images if the rotation invariant distance between them is smaller than some threshold, say epsilon. So small invariant distances means that images are similar, and we want to say, OK, they are connected by an edge. So what do we expect this graph to look like? So we have the sphere of viewing directions. And so we can associate an image with a point on the sphere. So up to an in-plane rotation, the image is completely determined by the viewing direction. And other images of similar viewing directions, if the images are clean, we expect them to have small rotation invariant distances, and so we expect to have edges between them in our graph. We don't expect to see an edge between, say, a vertex here and a vertex here. However, because of noise, we often make mistakes. That is, when we try to solve the registration problem, sometimes if the level of noise is bad, the noise is going to be aligned very well, but not the signal. And in such cases, what we really have are outliers. We have shortcut edges that are going to connect points that are completely distant on the unit sphere. And in some sense, one can view the cluster averaging problem as trying to separate, to distinguish between the good edges, the ones that correspond to our local neighborhood, from the bad edges, the shortcut edges. Now, this type of graphs in, say, network sciences or in sociology, they're called small world graphs. So for example, you can think of a network of just people over the globe. Usually, our friends are in our own neighborhood, so they live in the same building or they are in our same community or town. But often we also know some people very far away. So for example, Francois, I'm sure, knows many people in this university and Boulder as a whole, but he also has connections to people in France or in Israel and so on. And so he has some shortcut edges. In the cryo-EM problem, in the cluster averaging, what we'd like to do is actually to be able to distinguish between the two types of edges, to somehow denoise the graph in the sense that we want to remove these bad edges, these outliers. And so the way this problem is usually solved in network analysis is by counting structures. So what do I mean by that? So for example, counting triangles. So you expect a good edge in the graph to belong to many triangles. So all this if you have many local edges here, there are also going to be many triangles. However, a bad edge, a shortcut edge, for it to be a side of a triangle, you need two other random links that will make it into a triangle. So we can ask ourselves, for every edge, how many triangles this edge is a side of? And by this, to be able to distinguish between the good edges and the bad edges. Now, in fact, in the cryo-EM problem, we can do even better than that. There is a notion of what I call a good triangle or consistent triangle. So for that, if you consider three images that are taken from the same viewing direction, or you suspect them to be taken from the same viewing direction, when you align two images, it's not just the rotation invariant distance between them is small. While you do the minimization process and you try to find the best alignment, you also get the optimal alignment angle that I call your OIJ as an element of SO2, just a transformation, the in-plane rotation. And if you now consider the three angles, say the angle that aligns image I with image J, and then the angle that aligns image A with image K, and then the angle from K to I, these three angles should sum up to 0 modulo 2 pi. That is, you should complete a full circle. Or in other words, if you multiply the three rotations, OIJ by OJK by OKI, then it should be approximately the identity matrix. And so we should count not just any triangle in the graph, but only triangles that satisfy this consistency relation. Okay, but then one can ask, why do you stop at triangles? Why don't you consider cycles in the graph of length 4, length 5, and so on? And actually, how do you do it in some mathematically systematic way? So this is where I introduce vector diffusion maps. So the mathematical setup for vector diffusion maps is that the typical setup that usually people start with, that you have a graph. So you have nodes and edges, and it's an undirected graph. And the edges are described by some non-negative weights, Wij, to describe the affinity between nodes. So if Wij is large, then it means that node I and node J are very similar. So think of it as two images. They are very similar. Wij will be very large, let's say close to 1. And if they are very dissimilar, Wij will be close to 0. But in the cryo-EM problem, I just showed you that there is more information that can be used. Between any two images, we can also find the optimal transformation that aligns them. Let's call it OIJ. So in the cryo-EM problem, there are going to be elements of SO2. But in general, there can be different groups of transformations. And we'll discuss them later on today. Another question is, when I endow the edges of the graph with such linear orthogonal transformations, can I do a better job in organizing the graph? So in the cryo-EM problem, I want to be able to distinguish between good edges and bad edges. Maybe I want to do dimensionality reduction of the graph, for example, to embed it in a low-dimensional space. Or say I want to regress some function, study some function over my graph. Can I do it better by having this extra notion of orthogonal transformations? So now I'm going to confuse you a bit. So at this point, usually people get confused when I give the talk. So I'm going to switch gears to a completely different problem, not related at all to cryo-EM. And I want to show that in this very general setup, again, this framework of an undirected weighted graph with linear orthogonal transformations can be very naturally formalized and emerge very naturally. But this is completely not related to cryo-EM, so bear with me. So there is a problem in machine learning, or in general in data analysis, in a field called manifold learning, where one wants to study a point cloud in high dimensions. So we have n points, x1 to xn in Rp, in a p-dimensional space. So we have n samples in p dimensions. But the assumption is that it's not just an arbitrary point cloud that is scattered everywhere in p dimensions. The assumption is that there is actually structure, that the points are sampled from a low-dimensional manifold, a Riemannian manifold of d dimensions, where d is much smaller than p. So we have points in Euclidean space scattered. Where do my graph and weights and transformations are going to come from? Okay, so let me tell you how I do that. So there are going to be just two steps, very simple ones. The first step is going to be principal component analysis. I hope that many of you have heard it before. But I'm going to do it locally. What I mean by locally, I'm going to pick any data point, xi, in my data set. And I'm going to look at a ball of some radius, small radius epsilon, PCA. But I'm not going to tell you how I choose it now. But it contains only a small number of points. It is not going to contain the whole n points, my whole data set. And what I'm going to do is just to do local PCA, just PCA for a small number of neighboring points. And what PCA is supposed to give me, if I have enough sampling, it's going to give me an approximation to an orthonormal basis, that let's call it OI, for the tangent space at the point xi. So we call it TXIM. So we have the tangent space to the manifold at point xi. So if it is d-dimensional, then the basis should contain d vectors in Rp. And if I'm doing it right, I'm going to get an orthonormal basis. So I'm going to get, so this OI is going to be a p by d matrix. So we have d columns in Rp, where the columns form our orthonormal vector. So OI transpose OI is just a d by d identity matrix. Now, if the manifold was flat, like this floor, then all the subspaces that I get are the same. They just span the same linear subspace of Rp. And in that sense, all the OIs, they just span the same subspace, so that OI transpose OJ, if I look at that matrix, it should be just a d by d orthogonal matrix. Just how to transform from one basis to another. But if I have curvature, if my manifold is not flat, then as you can see, the subspaces, the tangent planes at every point can be different. There are different subspaces of Rp. And in that case, if I look at the matrix OI transpose OJ, it's still a d by d matrix, but it's no longer an orthogonal matrix. So what I do, just like in the Crowley-M problem, I'm going to look for the best orthogonal transformation, the best element of OD, orthogonal d by d matrix, that approximates this matrix OI transpose OJ in the Hilbert-Schmidt norm sense, or the Frobenius norm sense. It is the same. And I call it the alignment step. So we did local PCA step to find O1, O2, all the tangent spaces. And then we do alignment, but only between nearby points. Say that the distance is not larger than, say, epsilon. And I find this OIJ between such data points. And this OIJ is by construction, is an orthogonal matrix, and it can actually be computed very efficiently through the singular value decomposition of OI transpose OJ. Or for those who are familiar with the polar decomposition, it is the same. So I showed you some magic. You started with the point cloud, and from this point cloud I created transformations, OIJs. Geometrically, the way I would like you to think about these OIJs is that they approximate an operator that is known in differential geometry as the parallel transport operator. So this is a picture that I stole from Wikipedia, but the message here is that what is the parallel transport, say from xj to xi? So I have the tangent space to the manifold at point xj, and I have the tangent space to the manifold at point xi. Think of them as just two copies of Rd. So if my manifold is d-dimensional, every such tangent plane is just a copy of Rd. And I have a linear transformation from one tangent space to the other. What is this linear transformation? So say I have the tangent say I have a tangent vector here, the red one, and say this is the point xj, and say this is the point xi. What I'm going to do now is to parallel transport this vector from the point xj to the point xi in a way that the angles that it makes with the geodesic remain fixed, remain constant, while I'm doing the transportation. So I'm sliding this vector along the geodesic until it gets to the other point. And by construction, I'm getting a vector in the tangent space at that point. So clearly, all I did is just sliding the vector, so I didn't change its length. This means that the transformation is an isometry, which means that it's just an orthogonal transformation. So I'm trying to convince you that the OIJ that I get is an orthogonal transformation that actually approximates this parallel transport operator. Notice that this parallel transport is a bit peculiar. That is, if I transport from, let's say, from this point to that point, and then along this curve, geodesic curve, and then along this geodesic curve, and then I go back here, I'm not getting the same vector back. That is, it is now completely rotated. So if you look at parallel transportation over a closed curve, over a curved manifold, it's not necessarily going to give you the identity. So just to remind yourself, when I said here that OIJ times OJK times OKI is approximately the identity, is just because I'm looking at closed loops that are in something very small on the sphere. If I were to be able to align over very large loops, I would not get the identity back. So now what do we do with the weights, the affinities, and the edges and transformations? So we're going to build matrices. And the steps that I'm going to describe now are very similar to what, in the framework of those who heard about Laplacian eigenmaps, diffusion maps, as methods for dimensionality reduction that were developed by Belkin and Niogi and Koifman and Lafon. And so we're going to use something very similar to that. So we're going to construct matrices. So we're going to build a matrix S that is a symmetric matrix of size nd by nd. But really, I would like to think of it, and like you to think of it, as a matrix of matrices. That is, think of it as an n by n matrix where the elements are d by d matrices. So the ijth element of S is actually a d by d matrix, and it is going to be the transformation Oj after you scale it, multiply it by the affinity Wij, if there is an edge between I and j. And if there is no edge between I and j, just put the zero block. In other words, if the affinity is 0, just put the 0 block there. I write it in this way so you can realize that this matrix S in many applications is very sparse. Typically, we are not dealing with a complete graph. So the number of edges is usually proportional to the number of nodes and not quadratic in the number of nodes. And then we're also going to define a diagonal matrix of the same size, nd by nd, but again, think of it as just a block diagonal matrix where the ith block on the diagonal is a scalar matrix, the identity d by d matrix, scaled by the weighted degree of node I, where the weighted degree is just the sum of weights for vertices that are neighbors of node number I. So we have the matrix S, we have the matrix D. Both of them are matrices of size nd by nd, but we think of them as n by n matrices of matrices, of d by d matrices. And now we're going to define another matrix of the same size. I'm going to take the inverse of D times S. And I claim that the way to think about this matrix, we should think about this matrix as an averaging operator for vector fields over the data set. Okay, now let me explain what do I mean by that. So we have the matrix. Maybe I can. Now do you see better the blackboard, or? Okay, so we have this matrix D inverse S, which is an n by n matrix where the entries are d by d blocks, so it's nd by nd, and we can apply it to a vector, say to a vector v. And this vector v is also of length nd, and it has n blocks of size d, And let's say that the ith block, let's call it Vi. Or let's say this is the jth block. It will be easier. And now what happens when we apply the matrix to that vector? What do we get? So we get another vector of length nd. And again, we can realize it as n blocks of vectors of length d. But what is happening here? What is happening is that when I'm looking at I need to multiply that row by that vector. So I'm going to multiply, say, W, what is written here is Wij, Oij. I need to multiply Wij, Oij by Vj, sum, and then divide by dii, by the degree of I. So basically what is happening is exactly what is written here. I multiply Vj by Oij and by Wij. I sum over all the neighbors of I, and then divide by the weighted degree of node I. What does it mean? It means that I'm node number I. I'm looking at all my neighbors. Each neighbor holds some vector of length d. What do? You multiply by Oij. You do parallel transportation from j to I. So you parallel transport all the neighboring vectors, d-dimensional vectors, to your own frame. And then what? Okay, you do weighted averaging. You multiply by Wij and divide by the sum of all the weights. So what you do is it's just a weighted average of the vector field. So I call it a vector field because at every point we have a d-dimensional vector. It's not a function that we average, but actually a vector field that we average. So you can think of Vi as a vector in Rd that lives in the tangent space to the manifold at point xi. And now parallel transportation is crucial because if you just average the vectors without the Oij, without parallel transportation, it has no sense. You average vectors from different linear spaces. Before you can average them, you must have them live in the same space, the same Txim. You cannot average a vector from Txj with Txj prime. You must parallel transport before you can do that. So what we've just realized is that this operator, D inverse S, transport vectors from the tangent spaces Txjm that are nearby to Txim to Txim, and then averages the transported vectors in Txim. So indeed, it's an averaging vector operator for vector fields. And now we can finally define an affinity between nodes. So for those of you that heard about diffusion maps or other methods for dimensionality reduction, typically the way that you would like to assign affinities between nodes is by counting how many paths connect two nodes. For example, you set the length of the path, say 2, and then you count how many paths of length 2 connect two nodes. If there are many paths of such length, you want to say, these two nodes should be very similar. There are many paths that connect them. And if there are not so many paths, you want to say, they are really very different. They should be, if I want to do, say, embedding in Euclidean space, I should embed them very far apart. So basically, you do some kind of path integration. You count paths. But now we also have transformations, not just affinities, we also have transformations. So for example, if I look at node I and the unlabeled node here, I can see there are two different paths that connect these two nodes. And maybe when I look at these two paths, I get different transformations. So for example, I can associate transformation for this path by multiplying the Oijs along this path. And I can get a different transformation by multiplying the Oijs along that path. Now, if I get the same transformation, I should be very happy. That is, like with the consistency that I got with the images, everything is consistent. I want to say, these are really images from the same viewing directions. That I want to embed these two nodes to be nearby. But if I get completely different transformations, then now I'm not trusting the path very much. And I want to say, okay, maybe these are just outliers. Maybe the affinities are high, but are large, but what I get is wrong. So I want to count not just how many paths connect two nodes, but also the amount of consistency between the transformations that connect the path. So how do we do that mathematically? So luckily we have now the matrix DNA, so it can be done. So like I said, in the vector diffusion map framework, we define the affinity between node I and node j by considering all paths of length t. So t is a parameter, connecting them. But instead of just summing the weights of all paths, we sum the transformations. And as we said, every path from j to I may result in a different transformation. Just like we considered the parallel transport before, and we saw that different paths can give rise to different parallel transport over the sphere. And when ending transformations over different paths, cancellations may happen. So let's see how can we define the affinity between node I and node j as the consistency between these transformations. So the matrix D inverse S is not a symmetric matrix, but it can be easily seen that it is similar to the symmetric matrix S wiggle, where S wiggle is D inverse half S D inverse half. So D inverse S is just similar through a similarity transformation to that matrix. And now what we can do if we want to consider all paths of length 2t, so I'll explain why I choose 2t later on, we can take the matrix D inverse S and raise it to the power of 2t and look at the ijth block of that matrix. So when we take this matrix and raise it to the power, now basically we can now consider all paths of length 2t that connect node I and node j. So D inverse S raised to the power of 2t is a matrix of size d by d. And now I want to count how many cancellations or how much consistency I got. So I need some number, not a matrix. So how do I get from a d by d matrix to a number? I need a matrix norm to decide how big is this matrix. So the matrix norm that I choose is, again, the Frobenius norm squared or the Hilbert-Schmidt norm squared. Just taking the squares of the matrix entries and summing them together. Now, I want the affinity between I to j to be exactly the same as the affinity between j to I. And this matrix, D inverse S, is not symmetric. So instead, I use this matrix S wiggle raised to the power of 2t. And you can check that it just means taking this matrix, multiplying it by the degree of I, dividing by the degree of j. So intuitively, that's the affinity that I want to define. Mathematically, what does it mean? So what I'm going to show you now is that if you define in this way the affinity between node I and node j for all pairs, then this affinity is actually an inner product in a Hilbert space. So let's see that. So we know that S wiggle is a symmetric matrix, which means that it has a complete set of eigenvectors, and d of them. So VLs are the eigenvectors, and real eigenvalues, lambda I, again, lambda L go from 1 to nd. And I can order them in decreasing order of magnitude. And I hope that you've seen it before, that when you have a symmetric matrix, I can consider its spatial decomposition. So S wiggle ij, I can write it as the sum of the eigenvalues times the eigenvector at I times the same eigenvector of j transpose. And since I have this spectral decomposition, I can easily consider the spectral decomposition of the matrix raised to the power of 2t by just taking the eigenvalues and raise it to the power of 2t, but I don't have to do anything for the eigenvectors themselves. And again, remind yourself that VLI is a vector in RD. So I stands for the node, the vertex, and L stands for the index of the eigenvector. And now I want to consider the affinity. So we want to consider S wiggle raised to the power of 2t, the block ij, the Hilbert-Schmidt norm squared. So in order to calculate that, I have to take this matrix, multiply it by its transpose, and take the trace. That's the definition of the Hilbert-Schmidt norm squared. So instead of a sum, I'm going to get a double sum. So let's call the other summation index R. So L and R goes from 1 to nd. When I multiply, so I have lambda L, lambda R raised to the power of 2t. And when I multiply this matrix by the transpose and take the trace, I just get inner products. So VLI, VRI, the inner product between the two eigenvectors, any two eigenvectors, L and R, as realized in the tangent space number I, times VLJ, VRJ, just the inner product between them. I'll explain in a second what does it mean, but just from the algebra, you can see that I can write this affinity now as an inner product between two vectors of length nd squared, the vector VTI and the vector VTJ, where the vector vti is defined. So you can consider the mapping that takes node I and assign to it nd coordinates, nd squared coordinates, where the coordinates are given by lambda L, lambda R raised to the power of t, times the inner product between VLI with VRI. And then you can check that if you take VTI with VTJ, then you arrive at this formula here. So the affinities that we have here are just inner products in a finite dimensional Hilbert space. What are the coordinates? So if we think of the tangent space at node I, say Txim, and I have the eigenvectors, say V1i and V2i and V3i and so on, in order to get coordinates out of them, what you have to do is just take dot products between these vectors. And all possible dot products provide for you coordinates. Dot products are very nice in this setup because they are invariant to orthogonal transformations. So when I'm looking at the tangent space, I can get any, say I use MATLAB to get the OI, to get the basis for the tangent space. But what if MATLAB decides to give me some rotated basis? Well, I don't care because I'm just using inner products that are invariant to such transformations. So they're very natural in that setup. So that's how I get transformations, and I call this map VT the vector diffusion map, and it's actually a family of mappings scaled by the parameter t. And the reason that I choose 2t here is just to ensure positivity. That is, if some of the eigenvalues happen to be negative, then it's not a Hilbert space. So that's why I take 2t, although in many cases we can be sure to begin with that all of them are going to be positive. Now, once I'm in a Hilbert space, it's very easy to define distances. So remind ourselves that we have the vector diffusion map, and we have inner products. Once we have inner products, we define square distances. So the square distance between node I and node j is just going to be the squared norm of node I, VTI with VTI, plus the squared norm of node j, minus 2 times the inner product between I and j. So we have now a distance that I call the vector diffusion distance between node I and node j. Like in the diffusion map setup, other normalization of the matrix S are possible. I'm not going to get into it today. One can also very easily show that all the eigenvalues are going to be between -1 and 1. And typically we'll get a very quick fall-off of the eigenvalues. And especially if you raise it to the power of 2t, then the fall-off is even more rapid. What it means that if what I care is just an approximation to the vector diffusion distance, I can get it very easily by just computing the few top eigenvectors and eigenvalues of the matrix. I don't really need to take my sparse matrix and raise it to the power of 2t, and then it becomes dense, and everybody becomes very sad because no one knows how to store such huge matrices. Instead, I can do very efficient computation with my sparse matrix, just compute the top few eigenvectors and eigenvalues, and then I can get very good approximations to the vector diffusion distance. So let me show you an application to the QuaREM, what we started with. So this is a result of a simulation where we know exactly the viewing directions. So we made 40,000 we started with 40,000 clean projections of a volume. We added noise to it at a very high level of noise. The SNR is 1/64. And there is the before and after pictures. So what is the before picture? The before picture, for every image, we search for its 40 nearest neighbors in the rotation invariant distance sense. And what I show you here, because I did the simulation and I know the viewing directions, I can show you between any image and its 40 nearest neighbors, I know what are the angles between the viewing directions. I want them to be very small. I want small invariant distances to actually reflect similar viewing directions. But so what you see is this histogram of angles in degrees, and there are many, of course, that have small angles, many pairs that have small angles, but you can see a very fat tail of outliers, extending all the way even to 180 degrees, images that have completely different viewing directions, that should be like a reflection of one each other and not the same image. And then we applied the vector diffusion map framework. So I just told you how one can construct and compute the vector diffusion distances. And you can see that almost all the fat tail of outliers has been chopped off. That is, we do a much better job in detecting images of nearby viewing directions. So if here, like 50% of the images, with pairs of images reside outside the spherical cap of size 20 degrees, here's only, let's say, something like 5% of them that are outside the spherical cap. So we do a much better job in eliminating the outliers. And these are actually the cluster averages that you get from the real images, the one that I showed you that lead to the 3D reconstruction. So they look much better than the original noisy images that you get from the experiment. OK, now just a mathematical anecdote that is called the Harry-Ball theorem. So actually, I cheated you a bit about what Frank and Patrick are doing. And it's not really what they're doing. It's my view of what they're doing to make the introduction easier. Really, what they're doing, they take the data set of images, and the first thing they do, they rotationally align all images in a sense that they try to globally align all of them. So for each image, they try to find some rotation and rotate it, so that in some sense, they are in perfect alignment. I'm not saying what does it mean, but this is what they try to do. And then they define the rotation invariant distances just as the distances between images that were already aligned. So they don't really try to align every pair of images. But there is a problem with that approach. And the problem is that it is actually impossible to globally align all the images in the cryo-EM setup. And the reason for that is a theorem in mathematics, in a field called algebraic topology. It's called the Harry-Ball theorem. And what the Harry-Ball theorem says is that, if you read together with me, there is no non-vanishing continuous tangent vector field on the sphere. So what does this mean? So we have the sphere, and at every point on the sphere, like my hair, you can assign a tangent vector. And you try to do it in a way that this tangent vector field will be continuous. Well, it is impossible unless at some point you have 0. OK? So what is the implication for our images? So again, every image in the cryo-EM setup corresponds to some point on the sphere. And you can think of the x and y direction of each image as a vector field on the sphere, a tangent vector to the sphere. Now let's consider just the x-axis. If you are able to globally align all the images, it means that this axis is going to smoothly change over the sphere. But this is impossible. At some point, it must be 0. So there is no way to globally align all images over the sphere. So if someone tells you that here is a structure that I got from, I won't mention the toolbox, be more skeptical than usual. OK, now, in terms of the mathematics, so if you remember, in the title of my talk, I had the connection Laplacian, and I haven't mentioned anything about it so far. So don't read the whole theorem. But what I'm trying to say is the following. That if we now take more and more data points, if the points are sampled from my manifold, a d-dimensional manifold, and we sample more and more data points, so n goes to infinity, and the weights, the affinities, are taken from some kernel, for example, the Gaussian kernel, with some bandwidth epsilon, where epsilon is also going to 0, and the OIJs, the transformations, are just constructed in the same way that I described before, the local PCA and alignment, the two-step procedure. Then, in the limit that n goes to infinity, my matrix D inverse S becomes larger and larger. So it approaches some integral operator. But then I take the limit epsilon goes to 0. So the number of neighbors gets smaller and smaller. So it actually converges to some differential operator. And in some sense, I do averaging with neighbors. And then we can look at D inverse S minus the identity. So I'm averaging with neighbors and subtracting the identity of my vector field. So if you recall, when you work with functions and you average the values of nearby points, you average them, and then you subtract the value of the function at the point, what you get is the Laplacian. So for function of one variable, it's just a second order derivative. In general, you get the Laplace-Beltrami operator over the manifold. Same thing happens here. What we get is, again, a second order elliptic operator over the manifold, but not acting on functions, but actually over tangent vector fields to the manifold. And that second order operator is called the connection Laplacian. So it's not called a Laplacian because actually for vector fields and forms, there is actually more than just one kind of a Laplacian. Not like functions, there are more types of Laplacians. And what we are able to show, so this is work with Hauti and Wu, that at the limit, at that limit, n goes to infinity, epsilon goes to 0, you get convergence to this second order operator, the connection Laplacian. In the case the points are uniformly sampled over the manifold, if not, then different normalizations can lead to a similar result. And just to reassure that this is indeed the case, what we did is we sampled points in a uniformish fashion from spheres of different dimension. So this is the two-dimensional sphere, three-dimensional sphere, and so on, just 8,000 points. And what you see here are the top few eigenvalues of the operator D inverse S. And on the other end, you can actually do a calculation using representation theory and compute the eigenvalues and the multiplicities. So for example, for S2, the multiplicities are 6, 10, 14. So like the multiplicities you get for the spherical harmonics times 2, and no zero order 1. And indeed, you see here is multiplicity 6, multiplicity 10, 14, and so on. And similarly for S3, you get 4, 6, 9, and similar. So this is just reassuring us that we're actually dealing with the right operator. Let me skip the other applications to manifold learning and other applications. And perhaps I'll just summarize at this point the vector diffusion map framework. And if I have time, I'll just tell you very, very briefly how to get the 3D structure. Because so far I just told you how to denoise the images. So, summary. So the vector diffusion map is a generalization of diffusion maps. For those of you who know about diffusion maps, we move from functions over our data set to vector fields over the data set. And in some sense, we move from the hit kernel for functions to the hit kernel for vector fields. A different way to view it is a way to globally connect local PCA. So I'm sure that you all know that PCA is one of the most fundamental and useful tools in data analysis and signal processing. But it is much more powerful if you just apply it to portions of the data set and not to the whole data set as a whole. It is much more powerful if you apply it just to neighboring points rather to the whole data set that need not have a linear structure. If you apply it just to a small set of points that hopefully has a linear structure, then you are in much better shape. But then at different points, you get different subspaces. And you need some translator, some dictionary to tell you how to move from one PCA to another. And what I just showed is how to do it using the parallel transportation. For those of you who know the denoising tool of non-local means, another way to view what I just showed is how to incorporate into the non-local means framework rotations in a very simple manner. But it's just a comment for those who are familiar with that method. We introduced vector diffusion distance. That is a new metric for data points. It is different than diffusion distance because it is based on a different hit kernel. One can consider generalization to higher order Laplacian from point clouds, like higher order forms, like tensor, not just vector fields, or different kind of Laplacian, like the Hodge Laplacian. One can reveal topology of the data, for example, orientability. So one of the things that I didn't show today is that if I sample points from a manifold, it's very easy to decide if the manifold is orientable, like S2, or non-orientable, say like the Möbius strip, by just looking at the eigenvalues and eigenvectors of the connection Laplacian. It is a very natural framework whenever you have a data set and there is a group of transformations that apply on the data set. So here we start in cryo-EM, we have images and there is a natural group of transformations, just rotations. But you can work with 3D shapes and consider, say, rotations in 3D or other kinds of orbit spaces. And there are more applications that I didn't discuss. So I think that I'll skip the how to find a structure. I can get back to it at the very end if there are questions. Let me just tell you that if you want, I can also send the slides. And there is a list of references of what we discussed today. The most relevant one is the paper with Houti and Gu, who was graduate students with Ingrid Doboshi at Princeton, is now a postdoc at Princeton. And another paper about the orientability that I haven't mentioned. The paper about the class averaging application to cryo-EM with my student Jane, Yoel Shkolnitsky from Tel Aviv University, and Ron Yardani, who is now at Austin, Texas. And I would like to thank you, but also the funding agency, the NIH, Air Force, and the Sloan Research Foundation. So thank you very much.
So in cryo-EM, one of the difficulties is when you do class averaging is when you have outliers, things that are actually not particles, and they're completely going to skew your. Is this diffusion idea, does that allow you to identify such outliers and in some sense solve the outlier question?
Right. So the vector diffusion distance also allows you to just identify non-particles and throw them out. So yeah, so we do this.
Before you actually build a graph, or how does that actually work?
So you do it while you build the graph. So for example, if you set a threshold for the rotation invariant distance, so this kind of non-particles will actually much fewer connections, much fewer edges compared to other images. So just thresholding images that have a degree lower than say 10, get rid of them.
So in practice, you still have to compute mutual distances between lots of pairwise images, right?
Yes. So what I didn't say.
You have lots of projections. How do you do that?
Right. So what I didn't say is how we actually do it efficiently. So so the way we do it efficiently is we actually completely bypass the need to align any pair of images. So there's a few steps. So first, for every image, we find a rotationally invariant representation of it. So this means to represent an image in a set of features that, if you rotate the image, will not change the values of those features. I can tell you later how this can be done in a data adaptive manner. So for those of you who are familiar with something called the triple correlation function or the bispectrum, this may ring a bell. But we're able to find also short feature representation, so we don't need lots of features. So think of it as, now we describe every image, let's say, with 200 dimension, as a vector in 200-dimensional space. But now it's a rotation invariant features. Then one can do naively and find nearest neighbors for every image by just doing quadratic number of comparisons. This can take some time. So instead, what we use is our fast algorithms to find approximate nearest neighbors that are almost linear in the size of the data. So for example, if you had a one-dimensional data set, in order to find nearest neighbors, you don't have to do all pairwise comparisons. All you have to do is just sort, say in n log n, and then you can very easily define the neighbors. So you see that in one dimension, the problem of finding nearest neighbors can be solved like in almost linear time. And there is a recent algorithm due to Peter Jones, Vladimir Rochlin, and Andrei Osipov from Yale that is mimicking this idea, but can actually be applied in dimensions higher than 1. And so that's, in this way, we build a graph in a very efficient way. And then we just find the rotation between any pair of images, but only for pairs of images that we decided to be neighbors. So the number of in-plane alignments that we do is linear in the number of images and not quadratic.